All right, let's look at another 1D free fall problem. I like this problem a lot. I think it's a fairly elegant problem and we can learn a lot from it. So here we have two students on a balcony of height h above the street. One student throws a ball vertically downward at speed v1. At the same time, the other student throws a ball vertically upward at the same speed. And this question is asking us A, what's the time interval between when the balls strike the street? So they're going to strike the street at different times, right? Boom, boom. And we want to know what is the time interval between them. And then part B asks, what is the velocity of each ball as it strikes the ground? So this is one dimensional. We're not imagining a 2D projectile here. The ball is either thrown vertically upward or vertically downward at the same speed. So, yeah, let's just think about just quick diagram. Remember that diagrams help our brains to parse this information. So the students are standing on a balcony right up here. This balcony is at some height h above the street here, and one of the balls is thrown straight downward at v1, and then the other one straight upward at v1, and we're interested in when they hit the ground and how fast they're going when they hit the ground. So I know I'm going to be using my 1D kinematics here. I need to put a coordinate system on this whole situation. So I'm going to go ahead and use the ground level here as my x equals 0. And I'm going to use an upward positive sign convention. Okay. You could use downward positive. That's fine, right? The coordinate system doesn't change anything about the nature of the physics or what's happening. So, but once we choose a coordinate system, it's really important that we stick with it. So, I'm going to piece this out. When you come approach a problem like this, then it's easier to kind of do it in pieces. There are lots of different ways to, not lots, there are a few different ways to solve this problem, but I'm going to solve it by in a particular way. Maybe you would have thought of it, maybe not. I don't know. So if you have another route that you've solved this one in, great. You should be able to solve this a couple different ways. Solving the same problem multiple ways is a good way to achieve mastery. So if that's you, I'd say keep doing that. So let's look at part A here. And first, I'm just going to focus on the one that I'm calling the downward ball, the one that's thrown downward here. And one of the things that I want to first do with this ball is figure out how fast it's going when it hits the street. So that's what we're being asked for in part B. And if I have that information, I can use that to actually help me find part A. So in these problems, we don't always answer them in the exact order necessarily that they're asking the question. It just might not be how it kind of organically happens. So I'm interested in finding the speed when it strikes the ground. They don't give me anything about time here, but they do tell me the height of the ball as it starts. So I do know its displacement. So I'm going to think about maybe using my velocity in terms of position here. V squared equals V naught squared plus 2a x minus x naught. So this just says it relates the velocity of an object, right, of a particle to its position and acceleration. And I'm interested in that here. So the final velocity here, this I can call this my VF. That's what I'm after. Here's my VF. I want to know what that is. My initial velocity is given as this is the downward ball. So this is the one where I've got V1 downward. So my initial velocity is v1. Now it's directed downward, which was negative in the sign convention. So it's actually negative v1. I square that, so that negative sign is going to go away. Plus 2, the acceleration here is g. It's downward directed, which is negative. So I'm going to sub that in as negative g here. And my displacement, so kind of think about this here. My displacement going from h to 0, that's downward displacement. So my final minus initial, I could say here that my final position is at the ground, right, which is 0, and my initial position is up at h there. So I'm going to just kind of clean this up again here. VF squared is going to be then V1 squared. That negative sign goes away when I square it, right? And here I'll have um, 2, I'll do one more step here. 2 times negative G times negative H, right? So this VF squared is going to be actually equal to V1 squared plus 2GH when all is said and done. You've got to keep track of these signs when you use these kinematics equations. Remember that when you're putting in a velocity, a displacement, or an acceleration, those are signed. Always, always, always. And so those will have a direction, and those signs relate to the direction. Cool. So we have the speed at which it hits the street. Got it. Now we're going to determine the flight time. I want to know this because I am being asked in this problem to find the difference between the flight time. So remember that here I am talking about the downward ball. I just want to remind you here. That's still what I'm working on here. So the flight time for the one that was thrown straight downward. So there are again different approaches here, but I think I'm going to use v final equals v initial plus at. V final I've already found. V initial is given. Acceleration is gravitational acceleration. Time is the thing I want to find, right? So if I'm going to isolate time in this equation here, I have that time equals v final minus v naught divided by acceleration. So remember, I always start with a general equation and then take that general equation and write it in terms of my specific problem. So for instance, this equation here, this is a general form of the equation. And down below is when I start filling in the specific quantities that are specific to this particular problem. Similarly, this is a general kinematics equation. Even when I rearrange it, that's still general. This is not applied to my specific problem yet. I'm just rearranging terms. Now I'll go back and I'll actually pop in values that relate to my specific situation. So applying it to my specific situation, I'm going to call this T of the downward directed ball here. That's going to be V final. So, and in this case, that V final is downward directed, right? So that's actually going to be a negative value. So negative square root V1 squared plus 2GH. And that came from right here, right? That's where that came from. Then I'm going to continue on with the equation. Minus V naught. V naught in this particular problem is given to us as V sub 1. That is directed downward. So V1, if V1 is directed downward, then that's actually negative. And then that's all over the acceleration, which is, of course, downward directed. So that gives me square root V1 squared plus 2GH minus V1 all over G. So I distributed the negative sign in the G. Basically, that helps me to get rid of, if I distribute the negative sign in the G there, that gets rid of this negative sign and this negative sign right there. But I'm still left with one in front of that V1. Okay, so this is my time of flight. Now we're going to look at the ball that is, I'm going to call the upward ball, the ball that was thrown upward. Switch pages. So now let's look at what I'm calling the upward ball, and that's the one with V1 upward. And I'm just going to use the same approach there. So I'll find the speed when it hits the ground here. So V final squared equals V initial squared plus 2a x minus x naught. Same thing there. So V final squared is equal to, now this is thrown upward, so this is positive V1 squared plus 2 negative g. And then we have here the same displacement here of negative h. And the way you can interpret that negative displacement is that the ball ends up lower than it started, right? Regardless of that, whether it was thrown upward or downward. If you look at the overall displacement, the ball ends up at a lower point than it started, and downward is negative. So I know that my displacement has to be negative there. So VF squared is just going to be equal to V1 squared plus 2GH. That should look fairly familiar. And then VF is going to be the square root of V1 squared plus 2GH. This is actually the exact same thing we got for the downward ball. So interestingly enough, they both have the same speed when they hit the ground. This question is asking us, remember, for the time interval, though they will have different times. So let's look at the flight time for the upward ball. Flight time. And I'm going to remind us with a highlighter here again that this whole page here is about the ball that was thrown upward. Okay, so for flight time, I'm going to again use the same approach. V final equals V initial plus AT. If I solve that for time, I get time equals V final minus V initial over A. Again, that's my general equation. So my general equations are this equation right here, which is just the general equation. And then these are also general. They're not, it's before I have popped in any values for this particular problem. I've chosen my equations, but that's it. So if we're going to apply to our situation, I'll call this T upward for the ball that was thrown upward here. It will be equal to, now this V final here again is downward directed. It's still negative. So negative square root V1 squared plus 2GH minus V initial. Now this V initial, this ball was thrown upward. So this is positive V1 here. And that's all over the acceleration, which is negative G. So my time here is going to be root V1 squared plus 2GH plus V1 over G. So if you, let's go back just a second and remind ourselves what we ended up with here for this particular problem. I'll use a different color. We ended up with this as our final expression for the time for the downward thrown ball. So notice this negative sign in here. Now, if I go to looking at the upward thrown ball, this is our expression for time. There's a positive sign here. So what that tells me is that the time for the upward throw is greater than the time for the downward throw. That makes sense. Like if I had asked you to guess which one took longer, this is the one that you would have guessed took longer, right? So, and then finally, to express the difference between those two, then the difference in time, what they're asking us for then is going to be just this upward time minus the downward time. And then we could express that interval. And when we do that, the upward minus the downward, we have kind of a lot of cancellation, but what we're left with is going to be 2V1 over G. So our final answer there for part A, the difference between the time. And part B, we found this when we were solving A, and that is the final speed. Both balls have the same final speed. So they both have the same final, I think what it was asking for final velocity, right? So that's the speed with the direction. The direction would be downward, and which would be negative x in our sign convention. So the final velocity would be, if I'm going to write this as a vector, negative square root v1 squared plus 2gh. That would be negative, and you could throw an x hat on there if you want to put that in vector form. Okay, so hopefully this helped with this problem and makes a little bit of sense. There are lots of ways to do this problem too. So as I said in the beginning, experiment with some different methods and just make sure that you get the same answer to check your work.